Okay, we're picking up where we left off in the previous video, where we were going through the opening section of Chapter 2. Chapter 2 is on parallel lines, and this opening section is on the parallel postulate and special angles. Okay, now why this section is titled that, we'll have to see as we go, but here's the parallel postulate, just to give you a reminder. The parallel postulate was that through a point not on a line, exactly one line is parallel to the given line. So it's like here, you have a line, and there's a point not on the line. Well, there's only going to be one unique line that goes through that point that's parallel to the given line. And this is a result of our viewpoint from geometry from the Euclidean perspective, in that we interpret a plane as a flat two-dimensional surface in which a line segment that joins any 2 points within the plane lies entirely within the plane. That's the Euclidean perspective, and later in the chapter we're going to take a look at another perspective. But all of geometry in this course we study from the Euclidean perspective. Okay, so we left off here. So parallel lines and congruent angles. In figure 2.7, parallel lines, L and M, are cut by transversal V. So in the previous video, we learned about what a transversal was. It was just a line that is cutting across two lines, intersecting those two lines at two distinct points. So this wouldn't count as a transversal, cutting across two or more lines. But in a lot of cases, we're thinking about just like we're looking at zooming in on two intersection points. You need to think about a transversal. You need at least two intersection points you're looking at. So this wouldn't be a transversal. So we've got these two separate intersection points here. And that's where we identify we name these different angles: opposite interior angles, opposite exterior angles, corresponding angles, etc. Okay. And it was the case that also that the two lines, like all three of these lines are in the same plane. So you could think about maybe you had a case where there was one of the lines was kind of going into the page, but if these other two lines were in the plane of the page, then that wouldn't be a case of a transversal. You need to have all the lines, at least the three lines that are needed to get these two intersection points and these 8 angles, all be in the same plane. Okay, and so now what we're doing here is we're looking at the case, we're adding a constraint to this transversal case. We're going to say the two lines that are intersecting, let's think about if they're parallel. So you have a transversal, but with the two lines that it's intersecting are parallel. All right. So, okay, if a protractor were used to measure angles 1 and angles 5, these corresponding angles would have equal measures. That is, they would be congruent. Similarly, any other pair of corresponding angles would be congruent as long as L is parallel to M. So, okay, remember, corresponding angles was the idea that you could look at either one of the vertices, and you could think about a position of an angle around that vertice. So here you have top left, top right, or bottom left, bottom right. And an angle that corresponds to any of these angles would have, if you came to the other vertice and you looked at the same position around that point, that angle would be corresponding. So top left over here is 5, top left over here is 1. So 1 and 5 are corresponding. And bottom right, 4 and 8 are corresponding. And what they're saying here is that if you use a protractor to measure corresponding angles, you'd see they have equal measures. And so as long as L is parallel to M, keep that in mind. It's not the case if you do that over here, no. But with L and M are parallel, that is the case. And so we're going to state this as a postulate, so we're not going to prove this. Our intuition, if we measured with a protractor, that's not a proof, but that's good enough our visual intuition tells us this as well, that this is true. So postulate, if two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent. Okay, postulate. All right, in figure 2.7, L is parallel to M, and the measure of angle 1 is 117 degrees. So find the measures of the other angles. Okay, so yeah, what we can do in that case is if we know the measure of angle 1 is 117 degrees, then we know angle 5, its measure is going to be 117 because that's congruence and measure are the same. Okay, but then we can look at these vertical angles are congruent. So we can get, with that, we can see that angles 4 and angles 8 are also going to be 117 degrees. Okay. Now, what else can we do? We can, so, okay, we know that 2 and 3 are congruent and 6 and 7 are congruent. Okay. And we already know what 1 and 4 are and 5 and 8 are. But we know that if we sum the angles all the way around a point, that's going to be 360 degrees. So it's like what we're going to have is whatever these 1 and 4 sum to, okay, then if you take angles 3 plus angle 2, which is like 2 times some variable x, that's going to be equal to 360. So we can easily solve for those. And let's see if that's what they did. Okay, well, no, they use, there's other ways you could approach it. You know the fact that, so 1 and 4 are congruent, 5 and 8 are congruent, 1 and 5 are congruent. But then you know that like 1 and 3 are supplementary, 2 and 4 are supplementary. So you could use that. So there's multiple ways you could do this. All right, so several theorems follow from postulate 11. Postulate 11 was that the corresponding angles are congruent. For some of these theorems, formal proofs are provided. Right, because we're going to prove the theorems. Study the proofs and be able to state all the theorems. You can cite the theorems that have been proven as reasons in subsequent proofs. Yeah, okay. We're not going to go too deep into studying the proofs, but okay, theorem. If 2 parallel lines are cut by a transversal, then the pairs of alternate interior angles are congruent. So, yeah, if just to give some perspective on the idea of a theorem, we can see how this theorem can be proved because, okay, we use the postulate that that corresponding angles are congruent, right? So like 1 and, oh, I might have said that wrong. 1 and 5, oh no, that's right. Top left, 1 and 5 are corresponding. Okay. So, yeah, so we use that postulate, right? But then we also use that vertical angles are congruent. But then you can see as a result of that, if like we could see in general, it looks like it's going to be the case that opposite interior angles are always going to be congruent because you've got like these 2 corresponding angles are going to be congruent. Same thing with these 2. And then those two. But then when you add in the vertical angles being congruent, a natural result is that the alternate interior angles must be congruent. So you see how you can prove that, right? It's like a natural result. If the corresponding angles we're assuming are congruent as a postulate, and we know vertical angles are congruent, well, then it has to be the case that the alternate interior angles are going to be congruent. It wouldn't make any other sense otherwise. If that wasn't the case, then either the vertical angle theorem being congruent or the postulate of corresponding angles are congruent must be wrong. Okay, and so that's the idea. You'd go through an official proof that way. All right. So, okay, here's they go through the proof. And yeah, just notice that, this is kind of a different looking orientation, right? You see these 2 parallel lines. We're not going to go through the proof, but just it's important. I want to really stress as we go through this course that, you can think about everything we're doing is really in 3D space. It's just we're looking at on your computer screen, we're looking at a plane. We've kind of rotated 3D space to where we're looking straight on a plane. So you could draw any plane anywhere in 3D space. It doesn't even have to go through the origin. It could be anywhere. Okay, and imagine we're looking down at it. We're looking straight at it. We've rotated the origin, and now we're looking straight at it, and it's on your computer screen. So you could take any 2 parallel lines that are in that plane, and if they're cut by a transversal that also needs to be in the plane, then you've got this whole setup here. The angles that we're talking about are going to be in that plane as well. Okay? Although we did not establish that alternate interior angles 4 and 5 are congruent, it is easy to prove. Yeah, so this could be the case in general. They didn't prove for every angle, but yeah. So a theorem that is similar to the alternate interior angle congruence theorem follows, but the proof is not shown here. All right, if 2 parallel lines are cut by a transversal, then the pairs of alternate exterior angles are congruent. So yeah, just notice with these 2 theorems, it's not just 2 lines being cut by a transversal, it's 2 parallel lines. So just keep that in mind. So not only are alternate interior angles going to be congruent, but alternate exterior angles are going to be congruent. So if we come back here, right, we've got, this is why it's important to understand that notation with the corresponding alternate interior, alternate exterior, all of that. So yeah, let's come back to the previous page really quick. I want to go through this. So Okay, let's make sure we understand corresponding angles, because even I got a little bit confused. So the angles that lie in the same relative positions, such as above and left. Okay, so with corresponding angles, you look straight at the vertice. Look straight at it. And all you're looking at is, in that case, is those four angles in their relative positions. Up left, up right, down right, or bottom left, however you want to say it. Then you come to the other vertice, and you think about that exact same idea of upper left, upper right. If they have that same relative position, then those angles are corresponding. So bottom left is 3, bottom left over here is 7. Those are corresponding. Okay. Now you've also got the angles that are interior to the two lines cutting across. The 3, 4, 5, and 6 are interior, and then exterior to the two lines. 1, 2, 7, 8 are exterior. All right. Now you've got, let's see, alternate interior, which means that so alternate interior angles, you're considering just the 4 interior angles, right? By alternate, you're meaning that what you're saying is they're on the alternate side of the transversal. But 3 is alternate to 4. Well, but you switch vertices as well. So it's like a full alternation. You go from one angle, it's of the 4 interior angles, you switch vertices and go to the other side of the transversal. That's alternate interior. 3 and 6, 4 and 5. Alternate exterior, you switch vertices and go to the other side of the transversal, but we're talking about exterior angles. Okay, now, just to point this out as well, I touched on this a little bit in the previous video, but if we had a case like this, well, this is still, by the definition of a transversal, this is still, this is in the same plane. Let's say this is line V, okay? So now we have angles 9, 10, 11, 12. So by the definition of a transversal, this is still a transversal. So what's the notation here? Well, no, the notation that we're looking at here is based strictly on, you're looking at two separate intersection points for two separate lines. So here we'd have to go through all of this notation. We're not considering these 3 points as a unit. There's no notation for that. This notation is saying you're considering two intersection points corresponding to two lines that the transversal is cutting across. So we could look at, let's think about between line, you have transversal T and line R and V. Well, in that case, the interior angles are 3, 4, 9, and 10, exterior 1, 2, 11, and 12, corresponding 1 to 9, 2 to 10, etc. Or you could look at the 2 points between S and V. That's the idea. There's no notation for looking at all 3 of these points as a unit. We're not talking about that. I don't think we ever do in geometry, but we're not at the moment. We're definitely not. That's not what we're talking about. There's no notation for that. Okay, so yeah. So coming back here, we've got, if the 2 points you're considering, the lines that are cutting across those points are parallel to or they're parallel to each other, and the transversal cuts across those 2 lines, then what we've seen is that the postulate is that the corresponding angles are going to be congruent. We already know that vertical angles are congruent, but then as a result of those 2, that theorem and that postulate, there's 2 additional theorems that say alternate interior angles are congruent and alternate exterior angles are congruent. All right. Parallel lines and supplementary angles. When 2 parallel lines are cut by a transversal, it can be shown that the 2 interior angles on the same side of the transversal are supplementary. A similar claim can be made for the pair of exterior angles on the same side of the transversal. Okay. So here's just a strategy for a proof. We're not going to look at that. All right, so here's one of the theorems they just mentioned. If 2 parallel lines, we're still talking about parallel lines being cut by a transversal, then one thing I want to point out too, here, all of these theorems don't apply because none of these lines are parallel. T, S, and V aren't parallel. But if you did, let's say I drew V parallel to R, then you could analyze the 4 angles between those 2 points and all of these theorems would apply. right? So these lines are not parallel, so we haven't up to this point we haven't established any relations at all, other than the fact that these 9 and 12, 10 and 11 are congruent. That's the only relation we know between those angles, and that they all sum to 360 around those points. Well, and the supplementary, like 9 and 11 are supplementary, but nothing new. Other than what we know from what we've learned previously, we have no new information about the angles here. It's only when we say that, okay, we have two lines being parallel, that these theorems and postulates apply. So if two parallel lines are cut by a transversal, then the corresponding angles are congruent. Parallel lines, opposite interior angle congruent. Parallel lines, and same here. If two parallel lines are cut by a transversal, then the pairs of interior angles on the same side of the transversal are supplementary. So not the alternate interior angles, the non-alternate, however you want to call it, they're supplementary. And you can think about how this would be proved. This would be relatively easy proof. It's just a consequence of the fact that, well, if these two are congruent and these two are congruent, and then but these two are supplementary, then like the ones on the opposite end are going to be supplementary as well. So what they're saying is like 3 and 5 are supplementary. Add to 180. 4 and 6 are supplementary, and we're going to see that it's the same. It's the case that the exterior angles on the same side are also supplementary. So it says if two parallel lines are cut by a transversal, then the pairs of exterior angles on the same side of the transversal are supplementary. Okay. Okay, the remaining examples in this section illustrate methods from algebra and deal with the angles formed when two parallel lines are cut by a transversal. So yeah, we're going to just have to solve equations, algebraic equations, etc. And so, yeah, we'll work example problems. You'll get a sense for this. So yeah, they say that measure of angle RUV, these two parallel lines cut by transversal, RUV is some x here, and then WXS is this. Well then, look, that's opposite exterior angles, I believe, or no. Yeah, you have the 4 exterior angles. Opposite exterior angle means you switch vertices and flip sides. RUV, WXS, those are congruent. So you just set these two equal and solve. That's what they mean by algebra. You have to solve looks like a quadratic equation. And we'll work examples just like this too in the next video. In figure 2.10, lines R and S are known to be parallel. Thus, angle 1 is congruent to angle 5, since these are corresponding angles for R and S with transversal L. Okay, so R and S are parallel, and there's two transversals here. And so, yeah, here's an example where all these rules we're talking about, you just have to look at two separate points at a time. And what they're trying to illustrate here is that, well, this is kind of a mix in the sense that you have R and S are parallel, L is a transversal, and M is a transversal, but then L is parallel to M, and R is a transversal in that case, and S is a transversal, so there's a lot of intermixing here. You could use the reflexive, or I think it was called the reflexive property, where, well, since this is congruent to this, and that's congruent to that, then this is congruent to this, so, yeah. For L and M of figure 2.10 to be parallel as well, name two angles that would have to be congruent. Okay, yeah. So actually, what they're saying here, and what they're actually going for here, one of the things they're going for is, so L and M R and S are parallel, but we can go like in the other direction and try and prove that L and M must be parallel by analyzing the angles. That's another way to look at it. You could have the intermixing of angles if you also knew that L and M are parallel, but let's say we know R and S are parallel, but we don't necessarily know that L and M are parallel. Could we prove it, that L and M are parallel? How would we do that? Well, you could use everything we just taught, the theorems we just talked about in reverse. So for L and M to be parallel as well, name two angles that would have to be congruent. If we think of line S as a transversal, angle 5 would have to be congruent to angle 9, since these are corresponding angles for L and M cut by transversal S. So for L and M to be parallel, you would need, the opposite interior angles. 8 needs to be congruent to 9. and 9 needs to be congruent to 5. Those are corresponding angles. And that should be enough, because and if you can prove that, then that would be that might be enough to prove that they're parallel, because then we know that 9 is congruent to this angle for sure. And so, because you wouldn't have to go, to look at every angle, make sure it matches up, because at some point, as a natural result of, well, this is congruent to this, and this is congruent to this, and these are supplementary, once you prove a few angles are congruent, then it's automatically constrains the fact that the two lines have to be parallel, L and M. Okay, so given in figure 2.10, R is parallel to S and transversal L. Okay, measure of angle 3 is this. They give you measure of angle 3, measure of angle 5, and measure of angle 6. Find X and Y. So all you're going to do is just, okay, measure of angle 5 plus measure of angle 6 is equal to 180. There's an equation. Let's see. So you've got interior angles on the same side. Measure of angle 3 plus measure of angle 5 is 180. And then you have measure of angle 3 is equal to the measure of angle 6, opposite interior angles. So yeah, and you can just solve for X and Y. So, but we'll work examples like this. Note that the angle measures determined in example 3 are consistent with the required relationships for the angles named in figure 2.10. For instance, measure of angle 3 plus measure of angle 5 is 180 degrees, and we see that the interior angles on the same side of the transversal are indeed supplementary. Yes. Any example that we work is going to need to be in conjunction with all the theorems and postulates that we just talked about in this section, and they will be. Okay, let's work some example problems.